It's so tempting to sit on this. I'm not sure why it's so tempting, but it's like, oh, I can sit down and talk, right? I go like this, right? Pretend I'm sitting. Um, so the semester is progressing faster than we would like, right? Um, so half of you are wondering, have I finished grading? The answer is no. Um, I was a bad boy and took the week off. Or, well, I did spend 3 days going through transcripts, but that doesn't help you out. Um, there's only like 60 more transcripts to go, except today and yesterday and tomorrow. The admissions office is processing more of them, but transcripts. We get about 750 applications for the master's program every year. And they're like, when are you going to actually tell us whether we get in or not? And so you have to look at all the transcripts and say yes or no. I definitely thought about that. The problem is, and I actually have lots of data, but not all the data I need, because the transcripts, they come in as paper, and then they run them through a Xerox machine and get a scanned PDF. And it's not OCR, it's just pixels. And the information you want, some information you want is on the document. And so then it becomes writing a program to actually be able to recognize different. Yeah, no, we don't do that. It'd be nice. Because then you could, right? Literally, I have records going back 15 years of all the graduate students and all the grades they've got and all the courses they took. And then if I could then have a copy of the transcripts in a good format, I could then have a machine learning model, and then I could just apply it to the new student, and then I could overlook the results and say, oh, yes or no, right? Or there could be a probability. Yeah, this one's high probability, low probability. Then I just look at the middle ones. And no, you get to look at them all. Um, and so now we just use GREs to eliminate a bunch of people and then look at the people above that line. But no, it's not. Yeah. Oh, yeah, but everyone does it. And not only that, the GRE score has no questions about computer science, right? So there's nothing telling you whether or not this person has any aptitude for the field they're applying to. It's like, but if you go through 700 transcripts, you then realize why people do it. But so I haven't made much progress in grading. We do need to talk about a project, right? And so some people ask me, what do I mean by a project, and what scope should it be, and what should it be on? We have talked about machine learning models. So yes, machine learning, but since it's big data, it also would be useful if it was on Spark, because that's then you may not have data sets that need Spark, but at least it gives you some experience running machine learning models on Spark, or doing something else on Spark, so that you can say, like, yes, I have used Spark and I have used AWS, right? Because if the one thing you don't want to do is say you've got experience using AWS and not have experience running AWS, because then they'll start asking you questions like, well, I don't know. And that's a good way of not getting the job, right? Saying you know something. And so I really want you to use AWS and Spark. Um, So it could be, yeah, I'll find the data set and I will then do machine learning on it, or I'll do regression on it to investigate what I can learn about that. But there are other things you can do in terms of, well, for example, Python is supposed to be slower on Spark than, Java or Scala. So you could, okay, let me take this data set and I want to see, what performance difference there is, right? Or maybe you could do things like, okay, let's look at all the features where, Spark we have on PySpark and we don't have on, right, Scala or vice versa. Once we're done talking about Spark, we'll go on to Kafka, which is it's a distributed streaming service. There, the idea is, sometimes you have a big data set and you just dump it on a machine and then you crunch numbers. But there are other times when you're continually processing data, right? So if you're Walmart, you've got thousands of stores, and then you have the cash register, and every time now when you buy something at Walmart, right, that's sent to some place, and so you have this continuous stream of input coming from all those stores, from all those cash registers, and you want to be able to stream that into a central location and process it. You may want to have, how are sales doing this hour, this week, right? And so Kafka is a distributed streaming service. So if you've got millions of machines producing data, you can stream it to a central place, right? And it's distributed, so it can handle, it scales up. It's also fault tolerant, so if one of the streams goes down, then we can do something about, take care of that for you. And after we talk about Kafka, we'll then go on and talk about Cassandra, which it's a distributed database. Again, so it makes this so it can scale up better. But now you can put database on multiple machines, and it's also a NoSQL database, which, well, historically they were faster. So a few years ago, NoSQL databases were really, really popular because they go a little faster. But then, Oracle and Postgres and MySQL said, well, wait, okay, if you're a new competition, we'll what's the difference in a SQL database, NoSQL database? Basically, a SQL database uses SQL, and NoSQL database does not. That's a basic difference. But the reason people sometimes go to a NoSQL database is that for a SQL database, you define tables in advance, right? And tables have columns, right? And the columns have types. And so your data is pretty much structured. So you need to know in advance what the structure of your data is. What happens when your data isn't so structured, you don't know what it's going to be in advance, and it can change over time quite a bit. So a NoSQL database is like, okay, oh, you don't have that column? We don't care. Oh, you want a new column? Also fine. So so one common way is you just store things as a JSON, right? And so if a field's not there, it's not there. And you're not going to get the database complaining that you nulled out a field which was not supposed to be null. And so it tended to be faster, and it tended to be more dynamic, less structured. So then you have this database now which it's distributed, so it has high throughput, and now you can use that to input data to, say, Spark, and so you can set this Kafka stream to suck it out of Cassandra and push it into Spark. So you start setting up workflows of, having this data sources, streaming data into a sink, and then we can process the data. Right. So yeah, we can talk about, so one project could be a type of workflow like this. I can set up a Cassandra database, and I'll then stream it into Spark, and then I'll do some processing on Spark. You could do some performance testing between different streaming systems. Spark has its own streaming system. Kafka is supposed to be faster. Is it faster? No, I don't anticipate that people have. Well, one person might have a data set they have, but most people are not going to have their own data set, right? There are lots of places where you can find data sets. I didn't quite get the HTML correct. So there's a couple standard ones. Kaggle is a common place to find data sets. There's a lot of data sets. So I've got a link to Kaggle. Both Google and AWS have a set of public data sets, which tend to be slightly larger than the ones you find in Kaggle, because both Google and AWS have lots of storage space, and so they can have huge data sets. R has a set of data sets which are used mainly for teaching basic algorithms in R, but other languages use it too. There is a number of websites now which list a bunch of public websites that contain data, and they all like to call themselves awesome. So there's an awesome public data set, and it contains a big list of different data sets that you can look at. And the one I didn't get on here is UC Irvine is a repository for machine learning data sets. And so there are a lot of places you can find data sets to start looking for data, things you can do with them. The project you can do by yourself or teams of two. I don't like to use larger teams for a couple reasons. One is some people work, and so they really don't have the flexibility of working in a team. And so then it becomes sort of difficult when you've got teams of 4 or 5 or 6 people working on a project in a team of 1. And the other reason is if you got a team of 4 or 5 people working on a project in a class, there's a high probability that one of those team members flakes out, right? Anyone experience this? And then what do the other team members have to do? Yep. And then it becomes this cat and mouse game. How do you then how does the instructor find out what you did, right? And the other team members aren't going to rat on them, right? Because then they get you take multiple classes for them, and it may be, they're your friend, but they just got too busy or some reason, right? And so then you start getting this, taking the team members one by one and talking to them and say, what did you do? What did you do? And, it just gets hard. And so my solution is limit the size to 2. And it's harder when there's 2 people for one person to not do the work. And presumably people, when you select a single partner, you're a little more careful than when there's 4 or 5 of you. No, sure. No, I mean, you realize the entire class is now counting on you to ask all the questions. Oh, no. But they might send you a note saying, ask this question, but you're not likely to have it on the back of a check. Right? Right. So typically when you do Spark, you want to run it locally first to make sure your code works and it does what you want it to do. Because debugging things is harder on a cluster. Right? It just is, right? You get multiple machines, and so you make it run on your local machine first. Then you want to move it up to AWS and run it there, or on a cluster. And now it is possible to do things like you suggest well, I could have a notebook, and then I can use my notebook to drive what's running on AWS cluster. I haven't gotten that to work yet. I didn't try very long. It didn't go well the first go around. That doesn't seem to me a real necessarily productive thing to do, because if your job can be done in 5 minutes, you don't need a cluster, right? So if it's taking half hour, then do you really want to be interacting with a cluster while it's waiting for you to type things in? Usually you want to submit a job and get it done and then get the answer, and then, right? So someone else can get in the cluster and they can run it. So typically you would make it run locally first, and then upload your program and data and run it. Have a master on AWS. And since if you're running if your cluster you're running on demand, it could take 5 minutes for the cluster to spin up for you. When you run it locally, what it will do is it will run a master, and typically it will try and use all your cores. No, that's not a cluster. It's just running in local mode, and that's again, when you run, if you were to run the same algorithm using, say, I don't know, k-means on just using scikit-learn and using, k-means on Spark on your local machine, scikit-learn is going to be much faster than Spark, because it doesn't have the overhead that Spark does of trying to mimic running on mobile machines and having workers and masters. It's like, no, we're not going to have to deal with all this communication costs between all these different processes. Are just going to do it in one, and so it'll be faster. And when you run Spark on your local machine, right, you actually code and it's like, there were times like, okay, I have to wait a few minutes or a few seconds for this thing to, where if you just run scikit-learn, it's like it's done, right? Pretty much everything you've done is pretty fast. But even some of the stuff that should be fast on Spark is like, no, it's setting all this stuff up and it's reading this file and it's doing all this, and like you have to wait for a while, like, oh, okay, now it's done, right? And that was like, my data set only had 10 rows and 3 columns. It's like, there's overhead, right? I mean, this is a distributed system, and you're simulating a distributed system, and so there's overhead. You have to set up and um, yeah, it gets a little harder. Using notebooks is nice because then I don't have to worry about um, this format. I can just you turn in one thing, I can run it on my machine. Um, if you're using Spark, it's a little harder. You can run Spark locally, but you really want to also try and run it on AWS. Um, so what you can do is you can create a Spark notebook, right? And do it in such a way that you can take that code and run it on AWS. And then one way to prove it ran on AWS is you can then create it's the CLI command to run it from remotely, which you can only do once you run it on Spark on AWS. Yeah, but yeah, I mean it depends on what the project is, right? Now, it may be that you create a notebook with results in, right? I ran this, and here's my performance tables, and right, so you can write a notebook. The other thing that can be done is that when you create these machine learning models in Spark, you can actually save them to a file and then read them in later, right? Well, it makes sense, right? Because you spend all this time training a model, and then you want to run the model on various data sets, right? So you want to save the model so you can run it later, right? And that's another thing we haven't talked about. Scikit-learn is a very popular machine learning library. And so there are a number of places where they assume you're going to input a scikit-learn model. For example, Apple now has all their iPhones the last couple of years have a special processing unit on them to run machine learning models, which I think they've got like 12 cores and can do an amazing number of operations per second. And what you do is you train a model using various libraries. Scikit-learn is one of them, and then when you export it, you just import it into a iPhone app, right? And then it becomes a function you call. That's it. So the question is, does AWS have a Jupyter Notebook interface? Uh, AWS does, but I haven't been able to make it work. And it's been there for some time, right? And it's a public. I mean, so I assume I'm doing something wrong in the setup because no, you can do that. Um, but AWS already has you can log on to the site and say I want an EMR part, and then you say I want 5 machines running Spark, and they will install Spark for you. And Spark and Hadoop and various other things. You just say I want this, 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 and this, and this. And you're also supposed to be able to create a Jupyter notebook and then run a cluster from that. But I tried it and it didn't work. And you get this cryptic error message, and I didn't have time to figure out what I did wrong. But see, one of the reasons I want you to use AWS in your project is so you know how to do all these things. Do you have access to a cluster? Do you have access to a cluster of machines to do that on? You asked me, could we just create a virtual machine and put it and install Spark on it and run it on a cluster? Do you have 5 or so machines? Yeah, but do you have 5 machines to do that on? There's only one person in the room I know has a cluster that they can do that on. What? Do I? No. But I mean, you can go on AWS and just give me 5 generic machines, and then I will install. You create an image with whatever you want on it, and then you load that image on all those machines and do it. But they've done that for you for most things, and so it's like if you want to run Spark in AWS, it's already set up automatically for you, so you don't have to worry about all kinds of details you do if you do it by yourself. And you really, I mean, creating your own Spark cluster would be very, very educational. And we're an educational institution, but you have to be prepared to deal with a certain number of headaches. I mean, working with clusters can be painful. Things go wrong. You have to make sure all the software is somewhat uniform, consistent across all machines. Um, how does your program get distributed on the cluster? How does your data get distributed on the cluster? What happens when one of the machines goes down? And then when you get multiple users, you have to worry about how do you deal with people submitting jobs and making sure they're not all trying to run the job at the same time. If you've ever been a sysadmin, you'll know that running a machine can be slightly painful, and running multiple machines is. What's that? Yeah, yeah. clone. But was it a class or was it just for the team that was? Yeah, that's a good thing to do, but we don't have a. Yes, but you also usually want to run them on different machines. No, when I say machines, I'm talking physical different machines, right? Yeah, I mean when you go to a service which rents you web space with your web server or even AWS, when you say I want these machines, yeah, they're all using virtual machines or containers, right, for your work. Um, and that machine may be running multiple different containers, virtual machines for different people's jobs. Um, that's all abstracted away from us, right? When you, I have one small assignment to force you to use AWS. Um, we're actually almost done with Spark. Um, so you when you start doing your assignment and your project, you may want to read some of the Spark book to get more details. We'll then move on to Kafka. Um, there's a book out on Kafka, but I haven't read it. I just read the documentation. Um, Kafka is a much smaller system than Spark. Cassandra is a bigger system, so there's more documentation, more things to worry about. Yeah, but really need to make Spark real for you. And the only way to do that is to do it. And the first step is to run it locally on your machine. And then that depends on how I run it. So there's two ways of running Spark, right? One is you just type PySpark, right? And that all that does for you is it creates a instance of the Spark session that you can access with Spark, right? Um, so what I'll do in that case is I will have on the other window, right, the command to create the Spark session. So when I run across your project and it doesn't work because I can't find Spark, I'll know that because when I look at it, I won't see you creating this Spark object, right? Yeah. I just then create the instance of the Spark session and put that in the front, and then things should be normal, right? Because that's all that does for you is um, it creates an instance of the Spark session that you can use from Spark. Any other questions? Yes, we should start thinking. I mean, definitely. I mean, now the time to seriously think about it. And the one problem I always run up against is students delaying. I'm not sure what I want to do. I'll decide next week. And then next week comes, and oh, I'm not sure what to do. I'll decide next week. And all of a sudden, it's like, well, it's finals week this week. So the one question no one's asked is, when's it due? I always make the project due the day the final is scheduled for the course. I don't know what that day is, sometime in May, but if you look at the exam schedule, you can look the date up. Now, have you found any way to do DNA analysis on Spark? Yeah, I haven't either. Yeah, but I'm not sure anyone uses Spark to do that or not. So I've never seen anything written on. What's that? Oh, okay. That sounds about right. Yeah. So I've probably got a couple more lectures on Spark, and that's going to be it. Um, um, First, I want to, let's see, can I figure out, what's this one do? Back up a bit. Um, Agile software development is sort of, well, it was really trendy a few years ago, and we're sort of at the, it's things get popular, and then they sort of become normal, and then when they become normal, it's like, we need something else to be trendy. Um, um, yeah, and there was this manifesto for Agile software development sort of started all out, which is, it's 2001, which is almost prehistory now, right? Um, and it really was a reaction to how software is developed and how teams are being run and projects are being run. Like, um, I've known companies where they sort of considered software developers interchangeable parts. It's like, well, um, one case study where they ran the team into the ground, and the original team, everyone had left. They replaced everyone, and most of those people had already left. The company considered the project a success, even though they're like a year late, over budget, and everyone that knew anything about the project is basically gone. But they delivered a product, and like, okay, we're successful, right? And it's like, yeah, we just lost all the people and all the knowledge, and that's not good, right? Um, and so, yeah, people are more important than, right, the process and tools. Working software is more important than the documentation. Um, the contract thing is, well, I spent a year working at Bell Labs, And they had this story. There were times when people, they would submit, like, here, we want you to build, we want someone to build this piece of this hardware for us, and it's, here's the specs, and some wise guy would figure out a way of meeting the specs, and the hardware wouldn't work at all. And then they would sue Bell Labs for not, accepting their bid, because, like, I said, but it doesn't work. I said, no, it met the spec. You didn't say it had to work. So those contracts can be. The problem with contracts is that the software, it pits the software team against the customer, right? Because the customer wants to be as cheap as possible, and the company wants to be as high as possible. And so we're not talking about how do we get the best value to the customer, right, and satisfy both sides. And so that this contract negotiation is usually, there's going to be a winner and a loser, and each side is trying not to be the loser, which doesn't lead to good environment. And yeah, change. We're in a world that changes quite rapidly, right? Requirements change rapidly, and so, what happened? We have this grand scheme to plan what's going to happen in the next 5. This project is going to take 2.5 years. What happens when the world changes in those 2.5 years? And so they talk about, we deliver software continuously, early, right? When requirements change, well, okay, you decide you don't want that, we want this, so, and yeah, deliver it frequently, right? It's like, okay, we're not going to wait 2.5 years, and then we're going to say, here's your product. And yeah, you work together to make sure we're building what you want. Right, and so this is sort of what they're promoting. Right, so just being able to work as teams, trust your team. I mean, if you hire good people, you shouldn't have to look over their shoulder all the time. They're your experts, right? They should do what they. And so then, people are like, okay, there's an Agile manifesto of Agile data science. They're talking about, well, it's not like you just, the first thing you do works and you're done, right? It's like you have to iterate. You have to look at the data, see what it tells you, what it tells you, what'd you learn. And the data is going to tell you things, but it takes a while to figure out what that thing is, right? The story about, I told you the story about, I think it was Target. They discovered how to determine when someone was pregnant. That took a while, right, to find that out, right? That's why it's like the 25th query. It's not the first query. It's not the first thing you think about. It's not going to mean how you know what parameters to look for. Do you spend a lot of time just looking through the data, trying to figure out what's there? And the second one, right? It's like, well, if it takes you the 25th iteration to find something useful, if everyone stays in their office for all that time, right? I'm not going to get anywhere, because you're not learning from them, they're not learning from you, but you're just waiting, right? so yeah, we share what we're learning, even though we're not done yet, right? We're still exploring, but okay, I've learned this and this and this. It's not good enough yet. It's not what we want yet, but here's what I know. What have you discovered, right? Um, and I think this is the biggest difference, right, between what we do as computer people and what we do as big data or data scientists is that um, as computer people, we build things, right? We build an application, right? If you're an app developer, it's like, oh, that's simple, right? I'm going to build an iOS app to do this, that, right? Um, we set up databases. We may build a back end to talk to the database, so we can talk to the web page, right? And so we built this web page. We built the back end. It now works, right? And we write software to accomplish tasks. Um, but in data science and data in big data, you're trying to answer questions, right? Find out what's going on. And so it's a different type of activity, right? Yeah, and you have to figure out, I mean, what's the data telling you, right? If you're making some policy decision, you have to understand what the data is saying. Otherwise, um, you're just going on your intuition, your guesses. If you're building a product, you need to know what the data says so you can know what's going on. Um, And yeah, I mean, you start, I mean, with tables and data, and you have to clean the data and organize it, create data frames, and we aggregate and visualize, ask questions, so know what's going on. Then we start getting some sort of structure. We've learned this and that, um, and then okay, we can start sharing with other teams. We can start, it's like here's our findings. Um, and then at some point we can start, okay, now we now know how to predict when someone's pregnant. So now what can we do about that? Right. Right. You focus your time on the aspect of most essential to a success. But what is that? Well, we don't know. We have to experiment, right? Um, so it's really a different type of process, right? And this one's the hardest, right? Because as software developers, what we're used to is I built an app, here's the app, right? Oh, and maybe I'll write some documentation how to use the app, right? But if it's an app for a phone, like documentation, I mean, there's 3 screenshots, right? And that's it. Um, but here it's like, how do you have to document the process? I mean, here's how, when you go to the manager, you just can't say, look, here's how we can tell whether or not, right, woman's pregnant by what they buy. You say, here's what I did, right? Here's the process I followed. Here's my Jupyter notebook. You can now run it. I can now hand it to someone else to run, right? And they can then tweak it to understand what's going on. So it's documenting that process you went through, and you can repeat it, and other people can use it. So I just thought, coming back from break, we needed a, sort of ramp up period, right? Some, so I want to talk about linear regression. We talked about linear regression, right? And yeah, it's just, remember this, data, this Pearson correlation is, right? It allows us to estimate how good a correlation there is. And in Spark, we can do that pretty easily, right? It's just, well, I forgot the parentheses. So we can call correlation, right, and get so it's basically the same. It's a little bit different process. And yeah, we can, when we try and compare y with 1, one's constant, so it's flat line, which gives us, now, when we want to use regression in Spark, it's slightly different. Whether it's linear regression, any one of the regressions we can do, the difference is it uses this SVM format, which is different. And so, yeah, we get our dependent variable, which is the default label for it is label. It's like, I'm not sure why. And then independent variables is in a column called features. And those features is basically a vector of doubles. But usually our data frames have independent variables one column, and then each column for all your dependent variables, right? But now we want one column for all the independent variables. So that's not it. So here's my function. This SVM format stands for support vector machines, and that's so that you want the vector. That's why you want the array. It came out of Taiwan. It's a popular format, and it's basically one column for the dependent variable. Then it's crazy format. So here is, right, I took that earlier data and transformed it. So yeah, the first column is your label, your dependent variable, and the independent variable has only got one, and so it's 1 colon. That 1 means it's the first independent variable, and then that's the value. And then if there was more, then there'd be 2 colon, and then 3 colon, and 4 colon. So how do we do this, right? So we need some training data. We create your object, right? We fit it, evaluate it using all the same process we did normal linear regression, except we need this format, right? So right I created this data set, and it looks like this. Here's my feature. And there's a file, right? So it's and then to actually do it using linear regression, right? We need to read the file, create a linear regression object, and we can set various parameters. In this case, how many iterations we want to use to stop the whole thing. And then we just call fit on it, give it the training data set, and now we train the model. And then we can do, once we get the model, we can then take other data and say transform this data to see what it predicts, right? So the fun part becomes, well, measuring the model so we can do various things. The root mean square error, basically, we're looking at how, when we predict what the result's going to be, then we look how far that is from the actual value, and right. You take the square root of the square, right, to get rid of the negative positive values, and so we can now get some of that. And so we can compute that to give you an idea how, the smaller number, the better fit there is. The R2 value in this case is 1. Well, that's because it was a linear process and there was no random noise, so it should be perfect. And then once we got the model, we can read more data, and then, right, get the predictions, and then we can see what it's predicting, the features, and what the value is saying we should get. Again, the syntax is slightly different, right? The calls are slightly different. The big thing is, all our data is in this format. And the problem becomes you have a regular data frame. Regular data frames are not in that format, right? Okay. Like I said, we could call save on the linear model and it'll write to the file, and we can then later read it back in. I'll do the entire program, and now I can just read that model back in and use it. And the nice thing is you can save it on one machine and then load it back in a different machine. But yeah, the problem is what happens when the data is not in that format. I have that input file, right? How do I then run a linear regression on that data using Spark? Well, there's two ways of doing it. Using the R formula, another one using the vector assembler. And the vector assembler, basically, yeah, you create a vector assembler, you give it the input column, the output column, and then you can transform the data. And so here's an example, right, of creating the vector assembler. Here is the input column, basically the independent variables, and then the output standard is features, because that's the default value of the column for regression algorithms. And then you can transform the data, and then it's gonna create that. That column is now usable by the regression algorithms. So it's a step to do to, right, actually transform a regular data frame into something that the regression algorithms can use. And there's, right, the input file, so we get the X and Y, and then they add it doesn't have the colon in it, but the algorithms can deal with that. So here is an example of using two independent variables with some random noise, so things aren't exact. And here I'm reading the data, but I'm specifying the schema to remind you that we can either have it guess the schema, right, when you read it in, or we can tell, here's what the schema is. These are all doubles. for each column. And now I can create my vector assembler with, two input columns and the output column. And then when you transform the data, you get the features column, which the regression algorithms can actually use. So far, so good. We got linear regression, but we need to transform the data so it's in the right format. If you got SVM format, you're in good shape. If you don't, then we can either use the vector assembler, or we can use the R formula. And the vector assembler is where the input columns, what are the columns that represent your independent variables, and that'll produce the features column for you, which the regression algorithms will use. Right, and then I'm going to take the output and create a linear regression algorithm object, and then fit the data, and you can look at the coefficients, and it actually turns out to be. Yeah, I'm not sure. So the question basically is, if I'm doing linear regression, right, on a cluster, and so I've got 3 machines, and each machine only has like a third of the data. How do I then train? How do them all get trained? I'm not sure exactly how it's working underneath, because it's like I said, there's iterations, right? I mean, do one iteration, we keep on. I presume that after each iteration, there's a big shuffle, right? Because we need to know which makes it a lot slower than you think, right? Because if each iteration you have the shuffle going on, communication costs are much higher than CPU time, and that's why, unless you've got lots of data, using Spark is not going to work for you. Right? Is this going to? I mean, that overhead will kill you. It'd be faster using scikit-learn, right? Because you don't have that to worry about communicating between these machines in between each iteration. It's a good place to stop. The R formula is the way R does it. It's a bit more compact. It has a few more features, but it's also a bit more mysterious. It's like, y twiddle x plus z? Like, what does that mean? We'll talk about that on Thursday. What? No. It means that's the dependent variable and these are the independent variables.